A good way to think about a random process is that it's a series of random variables. For a continuous random process, for every t, there's a random variable, and it has a probability density function and all the wonderful things we talk about with random variables. And if there's another slice of time, two different slices of time, you have two random variables that have a joint PDF. And there are covariance and correlation coefficients and things like that. Just like when we talked about random variables and two or more random variables. And if also your random process is wide sense stationary, then all your first order statistics are constant. The mean is a constant. The variance is a constant. Meaning it doesn't, neither one depends on t. So by definition of x, for any x in a wide sense stationary process, it's this thing, which by definition was this. It's the expected value, it's the second moment. Expected value of x squared at a given slice in time minus the square of the mean. But this guy, for a wide sense stationary random process, is just the autocorrelation function argument of 0. So we have a way to calculate or find out what the variance is. For covariance, between a random variable at a time t and another random variable in that same process that is tau units away in time from it. So this is the covariance between two slices of time of that same random process that's wide sense stationary. You might not remember, but by definition, this is what the covariance is. If you multiply this out and do some simplification, you get this as the covariance. This is the covariance between two random variables in the same random process for a wide sense stationary process. And what's the correlation coefficient between two such random variables? Here was the definition. And here's what it is in terms of the autocorrelation function and mean of that random process. What does it mean? Let's see. Compare these two guys. These are two different autocorrelation functions. This guy's more spread out. It means this guy, 2 points of time, tau units apart, will be more correlated than than in this random process. So you would expect this random process to be smoother than this one, or this one to be more jittery, to change more frequently or faster than this guy. Do an example. The process is wide sense stationary, and it has this autocorrelation function. We're going to learn, and I'll just do a spoiler alert. It's going to turn out that if the limit as tau goes to infinity, if the limit of the autocorrelation function goes to 0 as tau goes to infinity, then the mean of the process is 0. I'll talk about that more later. So we know the two big things about this process: its autocorrelation function and its mean. So we can calculate its variance. Remember, it was this thing from the previous slide. And since the mean is 0, it's just the autocorrelation function evaluated at 0. We can calculate the covariance. From the previous chart, it is this. Since the mean is 0, it's just the autocorrelation function for every tau. And we can calculate the correlation coefficient between any two slices of time that are tau units apart. This from the previous chart, since the means are zero, it's this. And if you plug in this, these guys, let's see, the sigma squares will cancel. You have this e to the minus b beta part over 1. So that's what that, this is rho, I guess. Do another one. Random process is wide-sense stationary and Gaussian. And here's its autocorrelation function. Again, because this limit goes to 0 as tau goes to infinity, we know the mean is 0. Problem says, find the joint PDF for the following 3 random variables. Remember, it's 3 different slices of time, and these guys are just half the unit of time apart. 0, a half, and 1. And since it's stationary, it doesn't matter if those are the exact times. All that matters is the time between them. So what we already know, since it's Gaussian, all the joint PDFs are jointly Gaussian. And since the mean is 0, that's the same with every random variable in the process. They all have a 0 mean. In fact, they all have the same variance as individual PDFs. And they're going to have the same autocorrelation function evaluated at 0. That will be their variance for every random variable in the process. So all that remains, well, here's the joint PDF of the Gaussian. In our case, it's 3 variables. So this C is a covariance matrix, a 3 by 3. That's the only thing left that we need to find. Let's go about finding that guy. Here's what a covariance matrix looks like. And in our case, it looks like this. And since the variances are the same, all the standard deviations are the same. So all these sigma 1, sigma 2, sigma 1, sigma 3, they're all sigma squared. So we could pull that out of there. And what are the correlation coefficients? For the guys that are half a unit apart in time, it's this from the previous formulas. And for that first and last slice, which are 1 unit apart in time, it's this. And we can calculate those things from these guys. So we pulled out the sigma squared, and we've got all these correlation coefficients. And they're easily calculated. And there's the result. Or we could have just gone directly. Since these covariances, all the means were 0, all these guys are the autocorrelation functions. We could have just done that directly. Pull out the 100, and anyway, we get the same result. And this wouldn't have mattered if it was 0, a half, and 1, or if it was 10, 10 and a half, and 11, as long as they're the same distance apart. So you get that idea of different guys in the same process. And I think that's enough for one video.